Welcome to a lesson with Dr. Powell. Let's take a look at these two pictures and see how they relate to the rigorous limit statements that we have been discussing. It gives another viewpoint. In particular, when we think about the limit statements as as continuity statements for a function, if the whole or the limit is filled in. In particular, the value of the function here is equal to the limit, the two-sided limit of this function as x goes to this point. Let's look a little bit about the y value at this point and consider an epsilon going up and down from it. So we have kind of a sector of the xy plane that represents epsilon up and down from that particular y value. Now let's look at this sector and think about the shadow that it casts on the x-axis. So all the points in here that are in the sector in the graph, and see how it casts an image down here. In fact, we call this, what's cast down here, a pre-image, and we call the actual picture of the function that we see an image. So the pre-image is what comes before we plug in. We plug in and we get an image, that's the function. And what came before the image is called the pre-image. So this is a pre-image of that sector up here. Now, notice something about this pre-image and this point that we're interested in, where we're taking a limit as x approaches that x value, and we're getting this y value. Now, if we take this point and look at it in its shadow down here in the pre-image, notice that we have an open interval that contains this point. Now contrast that to this other picture where we know that the two-sided limit doesn't exist. The one-sided limit exists, but the two-sided doesn't. Look at the shadow that's cast from this point. This point is not contained in an open interval. It's an endpoint of an interval. So actually, we can use that idea right there to discuss continuity. If the shadow that's cast from the function itself to the pre-image at a point is an open interval, then we say the function's or it contains an open interval. That is because the pre-image actually is this and this over here, but it contains an open interval that contains the point. And if that is true, we say that the function is continuous at that point. That's just another way of saying a function is continuous, and it's a pretty rigorous way of saying it. Likewise over here, if since it's not, then we say it's not continuous at that particular point. And continuity has a lot to do with limits, because the value of the function itself, if it's equal to the limit of the function, then it's called continuous. So we're really talking about limits when we're talking about continuity here in this particular case. This is just another description. Notice that how this plays with the normal rigorous statement of a limit, because we first take an epsilon, a y closeness, and we see if there's an x closeness. So even like this, an open interval that's symmetric, an x closeness, such that when you cast its image up, you're actually within that sector. And there is, and so it works. And so we're good. But really, this is almost even intuitively a simpler statement to make. You take a point, you take the point in question, and you take an open interval about it, and you look at its pre-image from the function down here, and if it contains an open interval, then the limit exists to that point, or it's continuous. I mean, that's pretty much it. So that's kind of another way of looking at it, and sometimes that's a useful way. It's kind of like it catches jumps. Notice this type of idea will catch a jump. You can also use it to think about continuity on one side, or a limit to one side. If there's an open interval on just one side of it, just up to this point where it's an endpoint, then we can naturally think about continuity from the right. Anyhow, I hope this little description was useful and beneficial. And thanks for watching.